Okay, so my name is Adnan Mehonic. I actually come from academia and I'm a CTO co-founder of Intrinsic. So I'm afraid my presentation probably won't be as entertaining as the previous one, but I will try to make it relevant. So what do? We make a better non-volatile memory technology. So what is non-volatile memory? Well, in your any electronic system, you have many different kinds of memory technologies. In your mobile phone, you have, broadly speaking, something called volatile memory and non-volatile. Volatile one is for which you need to refresh it all the time. Non-volatile is something like your USB stick or SSD that you have in your mobile phones. And we need both. So why is it need especially pronounced now? Well, we talk a lot about computing. On the previous sessions, we talked about AI. AI fundamentally is a data-focused application. It's all about data. It's a number of weights in the models that you have for the AI. For that, you need to have a really efficient memory. And it's not only about AI in the context how we think about today, ChatGPT, LLMs. There's awful lot of stuff happening at the bottom. There is a big need to embed the intelligence where it's not today. So something like this, like my Garmin watch, I would like to have some very smart voice assistant that doesn't need to connect to the cloud. That today is not possible. Why is it not possible? Among the other things, memory is a big bottleneck. So that's basically what we are trying to solve. We are making non-volatile memory that doesn't need this refresh, but it has a lot of performances comparable to the volatile memory. So maybe let me just paint the picture slightly in more details, right? Give it some color. What is specifically problem with the current memory technologies that we have? Maybe some of you would recognize the plots that look like this. It basically shows how the size of the memory elements and transistors have shrinked over time, something like known as the Moore's law. Well, this is very much holds still for the logic. You hear about nodes 5 nanometers, 3 nanometers, 1.8 nanometers these days. That hasn't happened with non-volatile memory. Non-volatile memory that we can embed with the systems has stopped at 28 nanometers. So what does that effectively means? Microcontrollers we use in cars, in fridges, consumables, industrial applications are all kind of limited to 28 nanometers. And there is a big need to try to do something better. So then if you're thinking this is the taken apart the Apple Watch, not the latest one, but this is how the Apple Watch looks like. What the people need to do is something that doesn't look quite nice, which means it's not all integrated on the single chip. You would have a multi-chip solution. So when you take the Apple Watch apart, you would have the chip for the compute, for memory, and the basically inefficiency comes from this physical separation of the compute and memory. You are shuffling the data back and forth. For that, you pay a huge penalty for energy efficiency. Your battery doesn't last long. And the other problem is you can't shrink this memory. So I want to implement something quite exciting on my watch, but I can't because the size of AI model can't be employed on the size of this system. So what would help? Better memory technology, and that's exactly what we are trying, well, what we are solving in here. The technology that we are working with is called resistive RAM, also sometimes known as memoristive technology, and there is a many application spaces for this technology. But the simplest one, which is a really simple case to be made, people in industry understand this. We don't need to spend more than 30 seconds saying to people why is this important. It's the memory that shrinks where the flash wouldn't shrink. It is vastly more energy efficient, is faster than flash. And then that translates very nicely into what this would enable. So just a little bit about the story behind the Intrinsic. So we started really this sort of research program many years ago. I started in 2010. And then it kind of grown from there. We publish over 100 papers really on this topic. Nature, Science, all the papers, we can check the papers we published. But it was very much driven from that really deep knowledge in the technology where this would be relevant. So this really helped us to move fast in the sense that without maybe the amount of the investment we had, we managed to move much faster than our competitors. And today I believe we have the best technology out there in this space. So again, this is just what I said. If you don't believe me, you can take a screenshot of all the papers that we have published. It's a decisively simple device, but when you really go deeply into the tech, there is an awful lot of things going on. But our motto was, okay, science is kind of complex, and maybe there's a lot of things to be said, but in terms of how do you make this device, it's really simple. You go to the foundry, you say, this is what I need. It's a common material, silicon oxide. Everybody uses it. And it's simple, right? People just get that. But what is the product, right? There is this element that enables everything, which is our, if you like, a transistor, but it's just not transistor, it's called memristor. It's vastly better. But what is the product? The product is what we call a memory macro. That's basically the instance of the memory that any IC designer can use. So somebody designing headphones, Apple Watches, Garmin watch, Bluetooth headphones, can just use this memory, says I need the instance of 128 megabytes of memory. Here is the instance of that memory. Now I can start designing the rest of my chip. And this really helps. If you see at the numbers, it turns out to be 10 times faster than flash, 100 times faster in terms of the write compared to the flash. And that's a huge, huge benefit. It really enables, for among the other things, for AI to go where it can't go today. In terms of the routes to the market, we are not in the business making factories and foundries, right? That's very expensive. But there is a very well-established way how you can do this. So the piece of this equation, okay, here's this product, but you also need to, apart from other, let's say, what you would for the IC designers provide in terms of this memory macro, you need to have a qualified product. And that's why you need to go across both of these. You go through the potential manufacturers. So these are just examples of the partners. We are talking to many. I can't disclose which one we are in collaboration with. And then you go to all of these customers in here. So you will probably recognize a lot of these people who are producing all kind of electronic devices, again, in the consumer space, industrial space. Just a few words what this really means. So if you're really interested in numbers, it means at least 1/6 savings in terms of the system power, and then 10x in terms of the memory bandwidth. And it's really important. It's not just, again, for the compute and AI, it's as much about compute as the memory bandwidth. You really need to think about how quickly you can transfer that memory from memory to the compute. Sorry, I should say data from the memory to compute. There is a lot of applications out there. So I just mentioned, okay, maybe this class in here, which is variables, so thinking about all the different products, but there is a lot of things going on, autonomous vehicles. Typical car has more than 100 MCUs in it. All of them are on 28 nanometers. That's a problem. This technology could go there. There is, in terms of the power management, a lot of devices we use today, remote sensing. So it's really, really big markets out there for this. And I don't know how am I with time. Okay, so yes, maybe to tell you where are we at this stage. So for the last 5 years, we have been working with IMEC. Maybe some of you have heard of IMEC. That's probably, looking from the UK, the closest place you can go to be taken seriously. So what I mean by this, we innovated this, or we figure out this technology in the lab at UCL, but we needed to transfer it somewhere, which are industrially standardized platforms. And you can go to the foundry, absolutely. But if you still need to tweak the things, maybe prove yourself a little bit more, you would go to the places like IMEC. IMEC is a huge R&D facility in Leuven. It's a huge enterprise. The people like Samsung, TSMC, Global Foundries, all partner with them when there is a piece of R&D to be done. That's exactly what we did. We worked with the IMEC. We said, okay, here's our technology. We want to transfer it. We want to prove it on advanced nodes. We want to have our own bespoke test chip. And we did all of this, right? So this kind of hard work is already done. We produce the cells in millions. We characterize them. All the numbers that we have predicted, they've seen as the proof of the concept. All of that is done. The technology is incredibly reliable. These are our chips. So, okay, this is the wafer. So it's a big wafer you have. These are probably 200 chips also that you need then to dice and package. And once you dice them, it looks like this. You would package this. This is what we have done. And then after this, it's testing. anybody is interested, this is the other chip, right? This is what you call the layout. And again, for people who are not in the memory business, these numbers wouldn't mean anything, but just trust me, they are a game changer in the context of what it enables for the memory technologies out there. And maybe I'll just again finish with AI. I really see, I mean, when people talk AI about these days, it's really not all about these large models. It's not only about ChatGPTs and data center. There is plenty of things that are going in here. And what's the difference? Well, the main thing is this number of parameters. So, you know, these NNs, artificial neural networks, there's a lot of weights. Basically, these weights are parameters that you need to adjust. That takes a lot of memory. More weights you have, more interesting stuff you can do. But even if you don't have a billions of weights that you would need for ChatGPT, there's still plenty of interesting stuff you can do here. So this is sort of the obvious first go-to-market in terms of the AI, edge AI space. A lot of things in there. But then we are also, just because we are currently have the R&D programs on pushing this technology beyond. So really to go to the data centers, and we are currently working with the leading cloud service provider. Maybe you can guess who that is, but I can't disclose either. So maybe a few things about the team. So the team has been growing a lot in the last, especially 6 months. So this is, if you like, the management. So I said I'm the one half of the co-founder team. So the other co-founder is Professor Tony Kenyon, who has also been at UCL for more than 35 years. We have a CEO who is based in California, Zach Deary. We also have a subsidiary now in California, and around 6 people who are taking care of the business team in States. The rest of us are mostly in the UK and some people in Europe. So we have people in Belgium, in Spain, in Italy, in Germany, and soon maybe one other European country. And the team is really kind of diverse. Although it's a smallish team, it is divided to people who are looking like myself on materials, device development side of things, but also the people who are looking how to make the chips out of this and then put it in the application specific for AI, for example. We have 2 active programs on that. I think I'm going to finish with that, and this is a real photo. So this is the photo of our chips, right? This is not just some stock photo. This is actually the chips, and there is tens of millions of memory-stiff devices integrated in a single chip that looks like this.